This is going to be a very descriptive talk, not too much statistics, not too much analysis, basically just looking at pictures, which I love to do. There's my name and number in case you want to talk to me. This is a photograph I took off of the California Digital Library. If you look carefully at that cat's face, that cat looks very suspicious, and I invite you to be similarly suspicious of everything you've heard today. I tried to put a mask on my cat a few days ago, but she ran away from me. This is the source of my data, USA Facts. I went there about 3 months ago and I found that they had spreadsheets, so I started downloading them. It's one of the 4 or 5 sites that people have mentioned already today. So if you're interested in it, it's a good place to go. What I'm going to do today is look at the space-time analysis of the epidemic so far. If you look at this table on the lower left, we have 1 United States, we have 1 event. If you look at the top right, we have 6,000.
All right.
Hello? I'm hearing somebody else's voice. We're hearing singing. I'm hearing singing in the background. Sing-song voice. We had 700,000 cells in our data set. That's 217 days so far, and about 3,200 counties. That leaves you about 1.4 million cells in your database, and it's increasing obviously every day. This is a model or a flow chart of what I did. It's a simplification of what I actually did. All the work was done in R pretty much. I used QGIS for some of it and Excel for some of the others. So let's look at the temporal data. We've seen this data set many times. This is on the top are cases and on the bottom are deaths per day with a line shown beneath them or through them, as well as the week of the year shown on the x-axis. What I did was, the first thing I did was I looked at the death data, and this is several months ago, and I noticed this cycle, which many people have looked at. On the lower left is a residual analysis of that line, or is a linear regression. On the top right is a autocorrelation function, and we can see that there's a significant spike in deaths on Tuesday. I'm told that's because people often put off going to the hospital during the weekend, and then by Monday and Tuesday they show up at the hospital, and some of them are beyond help. But that's just something that somebody told me. Similarly, we see a similar cycle for cases, but the cycle is somewhat different. We see a spike on Friday. I'm told that's because case reports and lab tests fill up the labs of the hospitals and the health centers over the course of the week, and then by the weekend, Friday and Saturday, they try to get rid of all of the backlog of cases. So the daily data are not very useful. So what we're going to do, and what I've been putting up on my Facebook page, is the weekly data. Here is smooth. I use a decomposition filter on the cases and days, and this is as of a couple of weeks ago, I guess. So here's pretty much the data we're looking at. This is a daily count shown as a line, and then the weekly mean shown as a red dot per week. So that's the data I'm going to be using. That's the spatial. That's the temporal data. Here's the spatial analysis. This is pretty old. What I did was I looked at the logarithm, the population of each state on the x-axis, and the logarithm of the number of cases. Those are the black, and the logarithm of the number of deaths. Those are the red. So it's a compact way of summarizing all of the data for the 51 states in the United States. And those diagonal lines show the number of the incidence per 100,000, per 10,000, per 1,000, and so forth. So I think that's a very convenient way of understanding the differences between the states. But what we're going to be doing is looking at the counties, and here are the counties, here are the centroids. Essentially, what we're going to be looking at are the county polygons, as we call them in geography, and the centroids of those counties. I'm timing myself, so I'm trying to keep an act about 10 minutes. So here is a fairly old map showing in dark gray the number of counties with at least one death, and in light gray the number of counties with no deaths at that time. So you can already see that there's a considerable degree of spatial complexity going on just with the binomial or the 0-1 index. So if we look at all these counties per week, you can see this is a box and whisker plot that shows what's happening on each week, and we're getting a considerable variation between counties. If you look at that first week, week 10, I dropped out of about the first 4 or 5 weeks of the epidemic. You can see that we range from looking at the log to the base 10, we range from about per 100,000. So we range from about 1 per 100,000 to maybe 100 per 100,000. That's using the logarithm of the incidence. So I want you to keep in mind that pretty much I'm going to be looking at whole numbers, which are logarithms of the data rather than rates per 100,000 or per 1,000 or whatever. So here what I did was I looked at each state alphabetically, looked at the number of at the incidence per state on a scale of 0 to maximum. And here what I did was I fit a polynomial regression and then did a principal component analysis, and I was able to array the states from those states that have a kind of a beginning hump, New York, New Jersey, Connecticut, northeastern states, down to those states that have, through those states in the middle that have a very complicated kind of pattern with a mid epidemic hump, to the end of the data array where we're looking at states on the last row or so that have a much more kind of logarithmic or monotonic increase in their incidence. So we're obviously dealing with a very mixed bag. So what I've done is I've taken again, if you look at the second or third slide, we're looking at each of the counties, each of the days. If you lump all of those incidences together, we're looking at a cumulative distribution function of the logarithm to the base 10 with 1 in 10, -1 to the right, and 1 in 10 in 100 million to the left. And that gray line is essentially the cumulative distribution function, and it's pretty well behaved. And what you're looking at there are colors that represent the colors I'm going to be using in the mapping we're going to be doing. So here is as of a couple of weeks or a couple of months ago, mid July, what's called a choropleth map. Shows the incidence per 100,000, and you can see that there's a considerable pattern of like southern intensity, a blob in the Midwest. It's very strong northeastern, mid-Atlantic, the region where I'm living, and then a southwestern.
5 minutes.
5 minutes, okay. So what I've done is I've taken those choropleth data and made it an animation. So here what we're looking at is an animation week 8, week 9, week 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 30, and back to week 5. So that's the animation I intended to do in preparation for my final animation, but this is a so-called choropleth map. And it shows, among other things, a kind of an interesting hump in the Midwest. For example, if you look at week 10, each of the counties shown on a kilometer axis on the x-axis and the logarithm of income, we have a curious kind of hump in week 10 in the middle of the United States. And I don't really know why that is, but the animation is a very good way to examine that. But my original intention was to do spatial analysis and geostatistical analysis, which I have done. Here's an example of interpolated data. This is a spline, not a very good way of, my sister-in-law, who's an artist, said she looked at this map and she said it reminded her of pizza. I was going to color the lakes green and serve it as a as a meal. If we use kriging, we get a much smoother surface. So here is a kriging, and this is a geostatistical technique for looking at a surface, fitting a surface to irregular data, and it's very difficult to do. And it's, I mean, it's fairly sophisticated technique, and it takes a long time. So if you if you look at the logarithm into the base 2 of the cell size, it would take at a kilometer grid size about 1.4 days to run one of those interpolations. More appropriate would be something at level 3, which would be 2 to the third, which would be an 8-kilometer grid cell. So my conclusions, you have to look at space and time together. There's some very sophisticated techniques being developed by R for doing that kind of thing. And I'm beginning to learn them and beginning to use them, but at this point they're pretty complicated. You need to look at spatial patterns. That's one of the important points of looking at visualizations and maps and time series. I think there's very interesting patterns to be gone from those. I'm a strong believer of animation. When I submitted my talk to this day's event, I was afraid that there'd be 3 or 4 animations just like mine, but I was pleased to find that there were not any others. A scale is also important. You know, if you're looking at days, you're looking at times, you're looking at months, you're looking at years. If this thing goes on for a couple of years, we're going to have to be looking at a much wider range of temporal scales. We also have to look at spatial geography, grid cells, counties, zip codes, census tracts, census block groups. What's my next step? Well, to look at the geostatistics, to do a much more sophisticated job of analyzing the geostatistics, kriging, variograms, neighbor analysis, and so forth. I really want to look at a graph analysis of the pattern of the counties. What counties are next to one another, and does that propinquity have anything to do with anything? I think, a better incidence index. I think the log to the base 10 of incidence is a little crude. I've gotten some ideas. Maybe the negative binomial would be good. As I said earlier, I want to add to my list of tools the space-time R library. And finally, obviously, other data. I'm not sure I want to look at other data sources. The USA Facts is a good data set. Finally, I'm throwing out an invitation for anybody who wants to help me or anybody who thinks they could use my help. Put my name and email on the last slide, and I think I'm pretty much done.
Thank you.
Right.
There is one question.
Okay.
Do you have any plans to do COVID visualizations using physical media?
I'm not sure what you mean by physical media.
I'm going to request, I don't know either.
I could making a sculpture. That would be a way. I can make a COVID sculpture.
Let me see if Will Angel is still there. Maybe you can clarify the question. He says, Will says like Lego.
Did he visit my website and look at my Lego maps? I made some maps using Legos.
That's the reason this person is asked.
Probably. It would be fun though to get the kids together, some younger students together, and to use Legos to make maps and time series. And if you go to my website, ldecola.net, LDECOLA.net, you'll see a whole section of Lego visualization tools. So I think that may be where that question came from, but good to remind me. Thank you.
That is awesome. Maybe we should take this to the high schools and middle schools.
I definitely think that kids would like to benefit in some way educationally from getting down and dirty with COVID data.